Hello, welcome to the lecture on cell balancing in my Battery Management Systems course. And thank you for joining me in the transition to sustainable energy. Balancing might seem like an implementation detail at first glance, but there's actually a lot to it. So I've split this lecture into 4 videos. In the first video, we'll look at the causes of balancing and quantify those things so we can estimate the total amount of imbalance we might need to compensate for. In the second video, we'll look at active versus passive balancing. In the third video, we'll look at thermal design, an important topic for the electrical and mechanical engineers actually designing the BMS PCB and incorporating it into the battery pack. In the fourth video, we'll look at when it is best to balance, an important topic for the software engineers writing the control software and also for systems engineers. Okay, let's go. Cell balancing, loosely speaking, equalizes the state of charge among multiple cells in a battery pack. Let's look at why that's important. When we charge, ideally, all cells in a battery pack reach top of charge together, like this. Ideally, if our maximum operating voltage is 4.2 volts per cell, all cells reach 4.2 volts simultaneously. In practice, for various reasons, cell can end up imbalanced, or in other words, cells can have different residual charge capacities. Residual charge capacity is how much capacity in amp hours can be put into a cell by charging, or how far from top of charge it is. We'll discuss causes of imbalance in the next slide. When we charge, since all series cells are charged with the same current, the cell with the lowest residual charge capacity will reach top of charge first. We stop charging when any cell is at its maximum voltage, so some cells end up not quite full. Balancing restores the more ideal situation. An ideal balancing algorithm is one that results in all cells having identical residual charge capacity. Passive balancing does this by selectively discharging cells as needed so that their residual charge capacities match. Or, in other words, so each cell can take in the same number of amp hours before reaching top of charge. Imbalance has a few causes. First, we have self-discharge. All cells very slowly lose charge over time. If you put a cell on the shelf and check it a year later, you will find it at a lower state of charge. If one cell discharges faster than another, they will become imbalanced. Self-discharge increases with temperature, so a temperature gradient across the battery pack will cause an imbalance in the cells. Unequal loads also cause imbalance. For example, if the BMS utilizes multiple voltage sensing chips to measure the cell voltages, and if those chips draw slightly different currents, that difference will imbalance the cells powering one chip relative to the cells powering the other chip. Some internal defects or faults can cause high self-discharge in the affected cells, sometimes without propagating. For example, if you have a tiny defect in the separator, you might get a tiny local leakage between the two electrodes. Let's also talk about what doesn't cause imbalance. Capacity differences don't cause imbalance. I mention this because I've heard this idea, so I'd like to talk about where this idea comes from and what actually happens. Imagine 2 cells with unequal capacity. Here, I've drawn a factor of 2 capacity difference so we can easily see what happens. Let's start with both cells at 100% state of charge. As we discharge, the cell voltages deviate. When the smaller capacity cell is at 50%, the higher capacity cell is still at 75%. If all we look at is voltage, it appears that we have an imbalance. But we don't. The residual charge capacities of these 2 cells are identical. When we charge again, the 2 cells reach top of charge concurrently. In this section, we'll discuss causes of imbalance and quantify how much balancing current is required to keep a pack balanced. How much balancing current do we need? In the next slides, we'll estimate the magnitude of the effects for which balancing corrects. The balancing circuit needs to support at least that much. Cell self-discharge increases with temperature and is substantially higher at high state of charge than at low state of charge. This is kind of nice in that a nearly empty battery depletes itself more slowly than a fully charged battery. Here's the curve for one battery's self-discharge as a function of state of charge, and from the same source, an estimate of self-discharge with temperature. Let's do some math to get a sense of the size of currents we're talking about here. Say we have a 10 kilowatt-hour home energy storage battery, like a Tesla Powerwall. That's about 200 amp hours. Or an 80 kilowatt-hour electric car, also 200 amp hours. If a 2.4 amp hour cell self-discharges at 5 microamps at 80% state of charge, then a 200 amp hour battery will self-discharge at 417 microamps. Our worst case corner is at 100% state of charge and hot, say 45 C, where we estimate the self-discharge to be about 7 milliamps. Let's put those numbers into our table. Modern BMS chips are designed to have very equal input currents to minimize the imbalance caused by cell voltage measurement. For the BQ79616, for example, the measurement pin input currents are about 8 microamps and guaranteed by the datasheet to differ by no more than 2 microamps. For the LTC6813, the typical input current is a mere 1 microamp, and so we should expect the channel-to-channel variation to be smaller than a microamp. For the latest chips, the variation in measurement pin input currents is so tiny as to be generally negligible. Unequal loads can be more significant when multiple chips are involved. Automotive battery packs typically incorporate so many cells in series that a single measurement chip isn't sufficient. In this scenario, mismatch between the chip's supply currents matters. Chip supply currents are much larger than measurement pin currents. For the LTC6813, the total power supply current is the sum of several currents of some milliamps each. When the chip is actively running, it consumes around 19 milliamps, with a possible variation of about 3 milliamps. About half that current powers the ADCs, and the other half is for the communications interface. The BQ79616 is similar, though the variation for the communications-related half of its supply current is not provided. Let's sum up the imbalance resulting from our measurement chips. Imagine that the MCU queries the chips for their data. A common architecture is to have the chips in a daisy chain. Upon receiving a request for data, the first chip transmits its measurements, which doubles that chip's current consumption. Next, the second chip transmits its data, and the first chip passes it on to the microcontroller. Then, the third chip sends its data through the lower chips, and so on until all chips have transmitted their data. If we visualize that as plots of current consumption versus time, we might see something like this. Initially, everything is off, and the currents are near zero, some tens of microamps possibly. Then, the MCU transmits a short communication requesting chips to enter their active state, resulting in a power supply blip. Now, the first chip transmits its data with a corresponding current increase. Then, the second chip transmits its data, relayed by the first chip, with corresponding supply current increases for those two chips. Then, the last chip transmits its data, relayed consecutively by the other chips, with high supply current drawn by all chips. And the cycle repeats. The average current consumption for the three chips in this example are 12.5 milliamps, 15 milliamps, and 17.5 milliamps, which would cause a 5 milliamp imbalance between the groups of cells monitored by the top and bottom chips. The details will differ with the exact timing and number of chips. But this is a significant enough issue that many BMS chip suppliers offer an alternate architecture. An improved architecture entails a communications loop. The microcontroller can alternately talk to the measurement chips clockwise on one measurement cycle and counterclockwise on the next. This results in each chip transmitting the same amount of data when averaged over two successive cycles, and thus, nominally, the same current consumption for each chip. But with the loop daisy chain, each chip spends an equal amount of time in each state. But chips are not identical. As with any manufacturing process, we will see chip-to-chip variations. The max column of a datasheet EC table accounts for this. In this case, when we add up the datasheet numbers, we see 20 milliamp typical and 23 milliamps max for the supply current. A 3 milliamp variation. That variation comes from two main sources, some due to temperature and some due to manufacturing process variation. The temperature variation should be a small effect if the chips are all within the same battery pack. So mostly, we would expect the chip-to-chip variation to be due to manufacturing process variations, which is probably about half that 3 milliamps. Let's call it 1.5 milliamps. Let's put that 1.5 milliamps into our table. That's not a rigorous number. A more conservative approach would stick with the 3 milliamps from the datasheet. Our third source of imbalance was unequal current due to faults or defects. This one is tricky to quantify. How many cells leak depends on manufacturing quality, and often that is not truly known before manufacturing is in large-scale production. Also, determining what magnitude of internal fault to tolerate, and indeed compensate for with balancing current, and when to say, uh-oh, that unit should be taken out, that's hard. So, to be honest, I don't have a rigorous recommendation for quantifying the allowable magnitude of leakage current due to manufacturing defects. So, what do we put in the last line? Maybe we allow the same amount of balancing current for normal effects as to compensate for manufacturing defects? It's somewhat reasonable to allow our error budget to be of similar magnitude as allocated to expected variation. If so, then we might expect that in most packs, most of the time, the balancing current must compensate for less than 1 milliamp. And worst case, in a small fraction of battery packs, we may need as much as 17 milliamps of balancing current. Take a moment to compare those numbers to other currents around the battery pack. A car may see a 1500 amp peak current for a couple seconds. A typical continuous current may be 200 amps. For a 200 amp hour battery, 200A is a 1C rate. Even when the application load is not present, we may have a computer or microcontroller running, or possibly other peripheral loads. Tesla Sentry mode uses the power-hungry autopilot computer, drawing perhaps 600 milliamps from the battery. Car headlights might pull 175 milliamps at the battery. A 1-watt MCU monitoring a home energy storage system might pull 20 milliamps from the 50-volt battery. Cell imbalance is really quite small relative to those other application currents. Here, I plotted the rough numbers that we estimated on a logarithmic scale. We're looking at different orders of magnitude. As we discuss balancing, keep in mind that balancing corrects for currents that are thousands or even 1,000,000 times smaller than whatever the battery is powering. Let's summarize what we've learned about balancing. Balancing equalizes the cell's voltage or state of charge. Ideally, it equalizes the cell's residual charge capacity, or the amp hours remaining to top of charge, which is technically called top balancing. Some systems balance to another point on the curve. Balancing compensates for unequal discharge or leakage, including cell self-discharge internal to the cells and unequal loads external to the cells. The currents causing imbalance are small relative to other currents in the system. This is the end of video clip 1. Please continue the cell balancing lecture with video 2.